All right, so welcome everyone. This is the talk on effective Scala. I am Josh Suereth. No, I'm Josh Long. That's Josh Suereth right there. All right, so I am a software engineer, blogger, author, big nerd, and if you go to clout.com and check me out, I'm an expert in unicorns. Not sure why, but yeah, unicorns. So this talk is going to be a whole bunch of different topics encompassing Scala. So it might feel like a fire hose at times. If you need to stop me so that we can describe a particular topic, go into some more depth, just raise your hand and stop me. I'd like to kind of bring everyone along. Before topics, I'm going to ask how many people are familiar with certain concepts, and we'll dig in and hash out what we need to. So what is effective Scala? What are we actually going to be talking about? So this talk is to try to optimize your use of the Scala programming language to solve real-world problems without explosions, broken thumbs, and bullet wounds. Okay? Scala is a very, very powerful language. There's a lot of different paradigms you can use. There is a core to Scala that is nice and elegant to make use of. That is what we're aiming you towards here, to try to improve your code and kind of warn you away from some rocky areas. Like all languages, there are some rough spots. They are still useful rough spots, but you need to know when to use them, and we're going to guide you away from that until you know that you need to use them. So let's start with the most basic rule in Scala, and that is you are writing expressions. You are not writing statements. So what that means is in Scala, when I write a line of code, it is an expression that will return a value. When you think in Java, you think I need to make a variable, I need to execute something that will put something back into a variable, and it's very, very tied to how the machine operates, right? I'm putting things in registers, I'm running operations, I'm getting things out of registers. In Scala, I have an expression that returns a value. It's very, very mathematical. So here's an example of getting an error message out of an error code and how you would do it in Java, right? I would define a result of type string, and the underscore means it's initialized to the default, which is null. I match on the error code. If it's 1, I set the result to be network failure. If it's 2, I set it to be I/O. If it's anything else, I set it to unknown, and then I return that result. Well, that's not Scala. That's Java. That's C++. In Scala, notice how we don't even have to have a bracket after the equals for the method, because this is a single expression that returns a value. In Scala, most of your methods will most likely be, if you're writing nice, concise, abstract code, a single expression. So you don't need to use a lot of brackets in Scala. Anyway, we have the same match, but instead of actually assigning that match to the variable, we just have a value which gets returned if that particular case was true. And this function and this function are the same. They behave exactly the same in practice, but one is far less code. This is Scala style here. This is, if you get nothing else from this talk, learn to think in expressions. Here's another example. So if I have my domain model is people have addresses, and I want to find all the people in a city from some query that I pulled out. I can iterate over the people, I can iterate over my addresses, I can check to see if the city in the address is the same as the city I'm looking for, and then I can put that person into the found set that I created in the loop here, and then return that set at the bottom. Well, in Scala, we want to be expressive. That is not canonical Scala. We can do all this in one expression. It's called a for expression. I can iterate over all the people in a set. I can grab all the addresses. I can check to see if the address is a city, and then I can yield that person and return a value. So in Scala, you're doing transformations on your data. It's very, very, very good at modeling your domain and then ripping through it and finding stuff in nice, concise expressions. One thing I want to mention about for expressions is we have what we call the uniform return type principle. I'm modifying people from a sequence to a set because I want to return a set of people. So to do that, I have to start with a set, and then that for expression will yield a set. That's just one of the things about Scala, if you were curious why we have that additional code there. Okay, so the next thing about Scala, use the REPL. REPL stands for read eval print loop. This is the read eval print loop. If you type in Scala in the command line, you will get it. Inside of here, I can, oh, not in all caps, import things. Java util, concurrent. What's a good executors maybe? And then I can take executors and do something. Let's make a new single-threaded executor. Thread executor. There we go. Right, and so I just created a new executor. What the REPL gives me back is it gives me back a variable name to attach to the thing that was returned called res0. It starts at res0 and goes up unless I define my own variables. It tells me the type that was returned. Since we're a type-safe system, that can be important. I want to know what types are returned by methods and figure out how to make my types all work out. And then it gives me the toString of what it created. This allows me to rapidly prototype things. If I'm learning a new library, I can go read the API, and if the API is not clear, which all Java APIs are completely clear and outline every single behavior that happens when you call a method, so that's usually not a problem in Java. Well, anyway. So you can actually just start instantiating classes and run them. In Scala, the way you design code when or a new library is you will, in the REPL, start defining your classes. You will start defining methods. And you will start importing libraries and testing them. And so you can work out the kinks of your API before you even write a line of code. And if what you did in the REPL is great, you can check the history, copy, paste it into your source file, and now you're ready to go. So if you're coding in Scala and you're not using the REPL as part of your standard development, then you're not being as optimal as you could be. This is a really, really great way to work out kinks and figure out how things are, what's happening, how things work. Another good thing is almost all the build tools, Ant is the only exception. Maven, SBT, I think the other ones that have Scala support, you can run your build and then start a Scala REPL against your project. So you can instantiate all the classes and things in your project without having to type a ginormous command line. And it's usually one click, and it's really nice. Okay, another basic is stay immutable. If you read Effective Java from Josh Block, he says the same thing about Java. Immutability is really, really, really nice. There's a few reasons to stay immutable. If I have an immutable class or an immutable interface, I can just give this thing to any thread, and it's safe. I don't have to lock. If I don't have to lock, it means I don't have performance concerns accessing the data off of that class. If I can hash on my attributes, that's actually a really important one. If I'm using something in a hash map and the hash cannot be changed, I can actually create a really good hashing algorithm on an immutable object. On a mutable object, I can't actually use the mutable state to create a good hash. So I end up with some lame hash that just has nothing to do with the data in the class. My equality is really, really easy to do in immutable code because I can do referential equality on data if it's all immutable, and then go into deep equals, and deep equals is really easy to write. In fact, the compiler will do it for me if I make my objects case classes. It's safe to share your internal state. So one thing about Scala is we have closures. Closures can capture values inside of functions and defer them to other threads, defer them to other JVMs, because you can serialize them across the wire. If a closure is only capturing things from an immutable object, it's safe to go across threads and things. If you're using mutable state, you have to be careful with your closures to make sure you're not sending non-thread safe things to other threads. That's actually, if you use ACA, that's a common issue that people run into before they realize how to work with closures. The final reason is it's impossible to define anything as covariant or contravariant. if it is mutable. How many of you guys know what covariance and contravariance is? Okay, there are enough that we're just going to cover it real quick. If I define a array, actually let's do a list of anything, and I want to give it a list of integers, will that work? Anyone? Yes? No? Yes. If you type it correctly. If you use colon, that will work. So, if you type list 1, 2, 3, you get a list of int. I can assign a list of int to a list of any. Why can I do this? Because of covariance. An int is a subtype of any, and therefore list of int is a subtype of any. They're the same direction. Now, can I do this with a mutable list or a mutable array buffer? So let's import, actually I think I can just call array buffer. Array buffer is a mutable class, and it is under collection.mutable. So array buffer has mutable integers. So like the other one, I should be able to make a collection mutable array buffer of any and assign result 3, right? That should work. It's a collection of integers. I should be able to treat it as a collection of anything. No, that doesn't work. There's a specific reason. If I were to allow that on a mutable collection, when I mutate that collection and put more things in it, if I let you drop down and type, the person who has the reference to the array buffer of integer and the person who has reference to array buffer of any, if I start putting any's in on this side, this guy thinks they're all integers and I get class cast exceptions. So in Java, if you turn on all of your warnings and you follow them, you're actually not allowed to do any of this subclass, subcasing kind of things, the covariance with your collections, because it's actually dangerous. So in Scala, we will prevent that. If you want to use covariance and contravariance, you have to have an immutable interface. I can show you an example of contravariance. It's the exact opposite of covariance, and it's familiar from methods. If I have a method that takes any, I can override it with a method that takes, if I have a method that takes a string, I can override it with a method that takes an any. That is actually an example of contravariance. So the inheritance hierarchy goes the other way. So if we do that in methods here, I'm going to find something that takes a string and returns a string, and this is just going to be the identity function. And I can assign this to something that takes an any and returns a any, I think. I might have this wrong. Actually, I think it has to be this way. A nothing returns an any. Yeah, because it's inverted. Right, so contravariance, one of these variables is covariant, one is contravariance. Contravariance is the opposite direction. Arguments are contravariant. Nothing is the bottom type. Nothing is a subtype of string. I can take something, I can take a function where string is the one argument, and I can cast it to a function where nothing is the argument because it's contravariant. The arrows of subtyping are inverted. If you don't understand that, don't worry. You can read my book and it'll help you out later. It's not actually as important as you would think yet. When you get into talking about mutation, any sort of mutable setter is a contravariant thing. Any sort of getter accessing collections, that sort of thing, they're covariant usually. So I don't want to harp on this, but if you are immutable, you can actually make use of this subtype relationship. If you're not immutable, you end up having to copy your data into new objects to make sure that you are protected. And copying can be expensive. Also, immutability doesn't mean a lack of mutation. Here's a genius thing we do in the collections. When we are doing map methods and filter methods on immutable collections, sometimes it's more efficient to define a local mutable collection, do all of my mutation, and return the immutable interface. I am the only one who owned the mutable collection. I am giving up my reference, and now it's safe for people to treat it as an immutable collection. Safe to give to any sort of thread, and it's safe to treat it as covariant or contravariant or whatever. So that's actually a nice, beautiful thing that you can use to optimize particular methods. The downside is if you have developers who really, really want to use reflection, they could potentially break the fact that you want them to have only an immutable interface. So again, in Scala, if you're using reflection, probably not really writing the core Scala. You're probably doing something Java-ish. Okay, so next, use option. In Scala, we have a type called option. Option is a container of one or more values. Oh, can you guys see this? I know it's at the bottom here. You guys can see that? Okay. Option is a container of 0 or 1 values. If I instantiate option with null, I get this thing called none. So the possible states of option are a collection of 0 elements or a collection of 1 element. There's this option functor thing that you can use to take in an argument, and if it's null, it will give you none. If it's not null, it will give you some. The beauty of option is, in the type system, I am telling you whether or not I expect the value to potentially not be there. The difference between this and null is you can't forget to check. You've told the person this could not be there. And then I can start doing some nice things. Since these are collections, I can use for expressions. And let's say I have a servlet filter that wants to authenticate the HTTP session based on a username and password that I've parsed out from one of various locations. And I take in an option because the parsing may have failed, right? The parsing might be returning an optional state that it didn't succeed. Well, I can use this for expression to extract the username, the password, check if I can authenticate, pull in the privileges, privileges for .get returns an option. So it's the same thing in this for. So every usage of option is on a different line in that for expression, and at the end, I call the method I want to call. I'm now protected from null pointer exceptions, assuming people don't put null in option. That's also evil. Don't do that. So no null pointer exceptions. All right, next up is a little bit about Scala style. You know it when you have it. It's like quality without a name. Scala is not Java. We're not Ruby. We're not Haskell. These are the common languages that people come to Scala from. If you try to write Java in Scala, it will work. You can write that code. It's a great way to start learning Scala because you can still be productive. But don't pull your style guide from Java into Scala because there are things that you will get wrong that Scala will break on. It's a different language. Same with Ruby and Haskell. One of the things that frustrates me about Haskell has a big focus on symbolic method names, and Scala has the Java focus is on human readable names, so there's a big conflict there. If you're writing Scala and you want to make everyone happy, use both. But please prefer human readable names. That's my opinion. Anyway. Yeah, if you want more examples of style issues, my book has some outlines of certain ways that you do curly braces and things that can actually break in Scala because of semicolon inference. I don't really consider that stuff important. The real thing about Scala is when it comes to style, pick what's right for your team and enforce it with an automated tool. Don't make people go through code reviews where they have to change code. That's just terrible. It should just be an automatic thing if you want to force white space issues. And don't assume that Scala is Java, Ruby, or Haskell and pull in those kind of things into it. Redefine your style for Scala. Okay. On to object orientation. So if you have abstract members, you should define them with def. How many of you are familiar with the different types of members in Scala? Anyone not familiar, raise your hand. Okay, in Scala you have 3 types of members. I can have a value. A value is immutable. If I try to reassign it to 6, it's going to blow up. I can make a variable. If I try to reassign that to 7, that succeeds because it's a reference that can be changed. And then I have a method which will print line high and return 5. So every time I type X, I'll get 5 and it'll print high. Every time. It's a method. That happens to be a method of no arguments. If I have an abstract member, I should define a method of no arguments. Why? Because if I define it that way, my trait, X is going to return an integer. I think that's what we were doing up there. So I define trait foo, and I define class bar, extends foo, and I decide for class bar that X, well, we'll mark it as override. X really should be a value because it never changes in this class. That works. Now if I have a foo, that is a bar, and I call x.x, sorry for the bad naming, I get back 5, and it's always the same 5. In Scala, you can override defs with var or val. You cannot override val with, well, almost anything else. You cannot override var with anything else. Def is the most flexible, and the decision of whether or not it should be a member or a variable or a lazy val, which I didn't talk about, but lazily computes, it defers the computation of the val to later. That decision is an optimization of the class that you're designing. So if you use def in the abstract interface, you allow the implementers of the class freedom to choose what's the most optimal way to calculate their values. For example, if X is really expensive to compute, I want to use a lazy val here. So it will defer computation. Or if X is really cheap to compute, but I don't want to suck up memory, I'll use a def, that sort of thing. So keep them abstract. And here's an example of I define a bar method and I override it with a value. Also, that's fun because you can override toString with value. It's one of my favorite things. Okay. Next, you should annotate your non-trivial return types for your public methods. In Scala, I can infer the return type for a method. If I define foo and I give it 5, notice the type of foo returns an int. Every time I call foo, it's going to give me back an int. I didn't annotate it here. Scala inferred it for me. If I have a public method, and that public method, even though it's one expression, could be 6, 10 lines, I don't force the person reading your code to read 10 lines and try to guess what the type is that's returned for a public method. It's your public API. Document it. Put the return type. For example, object foo returns name. I should document that it's an option of string. One of the common things that gets messed up with using option versus non-option is sometimes you accidentally do a quality comparison on a string to an option of string, and that will always return false. It's a common source of bugs in Scala. If you document it, helps prevent people from doing this. Okay, another thing is composition can include inheritance. So should I have a has-a relationship or should I have an is-a relationship? In Scala, I can do both. I can define a logger, not the beer, and then I can define a has logger that just has a member called logger. Notice it's a def. It's not a val. It's a def, so I can choose how to instantiate it. And then I can later on define a trait called has awesome logger, which instantiates the awesome logger, overrides the logger member. This is a way where when I define my abstract class, I have a has logger method in my hierarchy that just gives me a member. And then when I want to compose my entire application, later on, I with in the has awesome logger trait. And I get the logger that I desire. If I'm in testing mode, I can make a dummy logger that doesn't do anything, or maybe it validates output against some value. So it's a nice flexible system. You don't have to give up inheritance if you want composition. So implicits. How many of you are not familiar with implicits in Scala? All right, we'll cover the concept really quickly. I can mark a value or a method as implicit. So an implicit value of an integer of 5, I mark it as implicit. What that does is now this value is in scope, and it has the implicit tag. I can define a method that takes a parameter list that is looked up from the implicit scope. So I want to look up whatever int is in scope, and I want to print it. So now if I call foo without parameters, it will implicitly go look up the parameters for that parameter list and put them in and return 5. So that's the implicit system in Scala. You have, and everywhere you code, you have this implicit scope where Scala will go look for values. I can define an implicit method that takes one argument, an int, and will return a new class with the method oh my, and this will print oh my. Yes, so now if I have an int, I can do int.oh my, and what the compiler does when I have a method call on a class and it can't find that method, it will look in implicit scope for any available functions that convert from the type that I have now to some other type that has that method. If there is one and only one in implicit scope, it will succeed. If I redefine this implicit as a foo2, so now I have 2 in scope, I get an error. It's ambiguous. There are 2 in implicit scope. The compiler can't help me out, so now I have to explicitly make that method call. So implicits are a way of making the compiler do more work for me so I can have less typing. The downside is that implicit scope, you need to know what's on it. When you're coding in Scala, the hardest part about coding in Scala is understanding what's on implicit scope and what kind of things I can call. Your IDE is going to help you out. If you press dot, you're going to see all these methods show up from things in implicit scope. But what you want to do as a programmer is limit what's on implicit scope so you don't have all that stuff running in your head. In general, in most of my code, there is absolutely nothing on implicit scope that I have to care about besides what Scala provides by default. And I'll show you a pattern that will let you add things to implicit scope in a way that you don't have to care about it. So it's very, very important to do this. One of the most abused features in Scala is the implicit system. And a lot of people run into problems with it and get disillusioned with Scala because they overuse it. It is not a magic lamp that you can rub that will solve all of your coding issues. So you write a X and then your entire program compiles. Right? That's not what it's about. So yeah, this is showing an example from my book where one use case for implicits is really awesome is say I have a library that I want to have in some sort of threaded context, but I don't really know what the threading context is. Say I'm running on a server and I need to make sure my threads don't stomp on each other. I can define my library, this is calculating the determinant of a matrix, to take in an implicit Java executor. It's an implicit parameter. So then, inside of whatever thing is calculating, I can define an implicit executor pool that is safe to run the calculation on. And now I can start calling all the methods in this library, and the context through which they are being executed, this pool, is implicitly passed. So this is a safe use of implicits because you're looking up by type. It's a value. It's not a conversion. And it can be a very, very handy way to pass a context along. The downside to this method is that you end up having this implicit context on all of your methods in an API. So if you end up passing something around too much, then this starts to fall apart. But it is very handy in a lot of situations. A lot of actual database transaction code, that's how they deal with the transaction. If there's an implicit available with the transaction, they join it. Otherwise, they'll create a new one, that sort of thing. So let's talk a little bit about implicit scope. This is where Scala looks. The important thing to note here is that Scala looks in your current scope for something that has a name that it doesn't have to access off of a package or an object. So there's no dot in the name. That's the first place it looks for implicit values. If I had defined this implicit val pool inside of another object, it would not have been in scope because it only looks in my current scope for things that it can access directly without doing additional work. The second place it looks for implicits is called the parts of a type. These are companion objects. Rather than worrying about this too much right now, I'm going to show you a pattern that makes use of that second part so that you don't have to worry about adding things into implicit scope that will cause danger later. So if we go back to our logger example, I define a trait logger. I define an object logger, and inside of him, I define an implicit default. What this means is anytime I want to look up a logger implicitly, it will grab the implicit one from the companion object by default, because that's the last place it looks. But what's beautiful about this is I can override it by defining one in scope. There were these 8 different places it looks. This is the last one. So I can override anywhere in my code what logger is used, but I get a default one. So now I have my log message method, and in my code I type logger.log, pass it a message, and it will implicitly look up the correct one for that context. I can override it where I need to. So this is a nice, safer way to start making use of implicits. You should avoid implicit views. Unless you really know you need an implicit view, you should avoid them. There are a lot of dangers with them. There are a lot of niceties with them. But from my own experience, I always avoid using them initially because there's usually a better solution that leads to the same elegance in code, but far more flexibility. Implicit views are extension methods, essentially, and extension methods can only go so far. They're not as good as other patterns. And implicit clat will get you if you... Okay. So you can use implicits to actually enforce type constraints. Scala has a pretty awesome type system, but one thing that I found really handy is defining really rich interfaces. If I have a buffer class that takes a buffer of some random type, but I want to support using this with Java byte buffers, so I want to have a conversion function to a byte buffer, that method should only be able to be called if that buffer happens to be of bytes. But I want a generic buffer class. So in Java, what I've seen done is people throw exceptions. That's not a really good solution. We'd like the type system to catch this for us. We can define an implicit type constraint. This funny less than : less than is actually a class. But it mimics subtype relationship constraints in Scala, which is less than : Scala will go look for this class in the implicit scope. The standard library provides you one if the subtype relationship is there. And so if that all succeeds, this compiles. If it doesn't succeed, it will tell you that T is not a byte. Yes?
I actually had an interesting problem. You're probably going to cover unit versus void later on. But I was facing the problem where I'm trying to define a constraint where the return of the function could be anything. When you're writing a functional line, the return of the function could be anything but unit. So in Java, it would be very simple. You just say, well, you check if it returns void, then it's messed up. But since in functional programming, everything always returns something, and unit is not a void, how can I...
So there actually is a value for. So the question is, how do I make a type constraint that can enforce only one particular type is returned, and that type, or one particular type isn't returned. That type is unit. There is a way to do that. We should take that offline. But first I want to tell you that unit is actually a value that is returned. It gets optimized away to void on the JVM for method calls because it's a not interesting value, but it is a value.
And that's my point. So it is a value. So I want to avoid that.
You want to avoid that value. There is a way. We should. Yeah. There's. Yeah. You can use implicits to do that. So. Type traits. These are a way of encoding interfaces that is immensely flexible. It uses the implicit system. So I define an interface, trait encodable. The interface is for some other type T. The use case for this is, say I want to define my own encoding, my own serialization mechanism, and I want to support Java lang string, I want to support Java lang collection, I want to support Java lang integer. I can define my own encodable interface, and then we're going to bootstrap how to encode collections in Java, how to encode strings, that sort of thing. I actually used this when I was at Google, and it works out amazing, way better than other solutions. So encode takes a T and gives you an array of bytes. Decode takes a byte buffer and gives you back a T. T is the whatever parameter is to encodable. My API for this whole library is the object, the companion object, takes a T that has an encodable context. The encodable context means somewhere in implicit search, I find an encodable for that type T, whatever T is. So if I pass a string into encode, it's going to look for encodable string. If I pass a collection of ints, it's going to look for an encodable of collection of ints. And then we look that encodable up on the implicit scope and call the encode method from that encodable. Okay? Now I need to define how to encode things that I don't control from someone else's library. Inside of that same encodable guy, I can define an implicit object, intCodable, that extends encodable int, and he will get looked up by default because he's in the companion object for encodable, based on how implicit search works. So I define how to do int, I define how to do collections. Here's an example of Scala tuples that's the same as how you would do Java collections. If I want to do a collection of some random type A, we'll say a collection of int, I would define implicit def, and instead of tuple, that would be collection encodable. And it would take an A, and it would then look up the implicit for A, for how to encode A. And then the collection can use this abstract way of encoding A, and just serialize in the A's however it needs to. So I am bootstrapping. Essentially, I'm bootstrapping and inserting classes in my hierarchy after the fact. So this is called the type trait pattern. It comes from C++, Haskell, some other functional guys, and it's really, really ridiculously powerful. One of the really cool things you can do is if I'm defining my own library at the same time, I'm going to define my own trait, and in my companion object, I can add how to encode things. So if somebody defines this encoding library, and I'm using it, I can add my own implicit object that will get looked up by default for my type if I put it in my companion object. So this is how companion objects can be really, really powerful and awesome. And if you put your implicits in there, you don't have to worry about it as much. You end up, when you need to figure out what's on implicit scope, you look at the companion. What's really cool about this is because of the way implicit scope works, remember we had two different areas we looked. If somebody screws up the encoding for collection, and I think I can write a better, more efficient version, I can override locally. I can define my own implicit value just for collections for encoding, and if I put it at a higher precedence level, my version gets picked over the library's version. So I can start overriding things. And that becomes really, really, really powerful. The other thing you can do with these is you can use them to define roles. An example here is if I have a synchronize method. Synchronize, it started off with I wanted to synchronize a directory to another directory. Right? Directories are files. But I kept mixing up the source and the sync. So if I define an interface for source and sync as type traits, I can make sure that the from, which happens to be a file that has an instance of sync, and the to, which happens to be a Java util file, which is an instance, from that's an instance of source, and to that's an instance of sync, I can make sure that I don't accidentally call the wrong API, but I still return files at the end of the day. I still preserve the fact that it was a file, but I'm treating one as a source and one as a sync. And then I can add in other things like, I can resolve from a website and use some web crawler as a source, but not a sync because I can't push, that sort of thing. But this is a way to preserve roles. So if something can extend from two different interfaces, but I want to make sure in my code I only treat it as one, type traits are a good way to do that. And they're basically the Scala way to monkey patch classes. It's type safe. It's nice. All right. So in the type system, to correlate with that, you want to preserve your specific types if you can. If you're taking in a value and returning the same value or some morph of that value, you want to make sure it's the same type. If I take in a file in that synchronized example, I should return back a file because I know it's a file. So the type traits are a good way to do that. There are other ways to preserve types in the type system. Here's a good example. If I take in a sequence and return in a sequence, well, what if I pass in an array buffer? Shouldn't I return back an array buffer because I knew it was an array buffer when I took it in and manipulated it? Well, yeah, I should. So we add a type annotation to preserve what came in and return that same value. If I take in a sequence and return an integer, then I don't need to preserve the type value. Right? It's only if I'm returning something I should try to preserve that specific type so that people can be knowledgeable about what you're getting. Again, in the book, I cover how you can actually optimize your algorithms based on what type you take in, but still have it be generic on T. So that's a pretty fun thing. Another thing about Scala, you should know your collections. This is the collections hierarchy. It's pretty awesome. Traversable is what we call internal iterators for collections. Anyone know the difference between internal, or not know the difference between internal and external iterators? Okay. Internal iterator, the collection itself can iterate over its values. It's the one who knows how, and it controls when it iterates. External iterators, which is iterable, is where I have an iterator method, and I get an iterator that I can control, but the collection doesn't. He doesn't know when I'm going to be done. The beautiful thing about traversable being at the bottom is I can make use of almost the entire collections API, but I can also handle resources. So I can define a collection that opens a file, reads in some values, and returns them when it iterates, and then closes it when it's done. And it's guaranteed that it knows when traversing is done because it owns the iterator. It's an internal iterator versus external. So that's the difference between traversable and iterable. Then we have sequences, sets, and maps. Hopefully those are familiar. The only new thing here is we have index sequence and linear sequence. Linear sequence, if you type list in Scala, is a linear sequence. It is a linked list. Linear sequences are things that you can decompose the head and the tail off of really, really efficiently. This is important if you're writing tail recursive functional programs or functional methods. You normally need to do really efficient head-tail decomposition. List is your data structure. When you come from Java, you're used to asking for array list all the time. This is not an array list. This is a linked list. If you are indexing into it, or you are attaching things on the end, it is O of n. It is a very inefficient indexing collection. It is very efficient for doing tail recursive programs. Index sequence is what you want if you want efficient indexing. If you want efficient indexing, you should use vector. Vector is a immutable array-ish collection that has efficient indexing, efficient prepend, efficient append. It's pretty much the go-to collection in Scala. If in Java you would have written array list, in Scala you write vector, and you'll get good performance. Again, if you need to go mutable, array buffer is the array list from Java, so knowing those different guys is important. So that's the collections hierarchy. I did a reflective call on all the methods on the collections. If you look, there's quite a bit. We're not going to go through them all, but there are some pretty awesome methods on there. The most used library in any code I've ever written is the collections library of that language, or a helper collections library. It's code that you use all the time. Scala's collections library is very rich. Most likely it will have some function that does exactly what you need if you look for it. If you don't know to look, you don't have to learn all of it at once because some of them are just simplified versions of slightly longer hand method calls, but it's a very, very rich API. Highly recommend learning it slowly over time because it will improve your code. Yeah?
Is there any reason why all of these besides this three are not lazy?
Why all of these three besides are not lazy? So collections have a view, which is lazy. So I can take a list 1, 2, 3 and call .view. Now I have a lazy collection, and I can map this and add 1 to every element, or add 2 to every element, and it doesn't execute yet.
Right, but you cannot consume into that view. You have to have a list to that view, right? So you cannot say that you consume something. So it's only stream that you can
Stream can lazily consume, but it does memorize, so that's dangerous. If you want to lazily consume something, you should use a traversable that you define, don't iterate over it, and then call .view. That's actually a really good pattern. I use that a lot. So I can define, the file example. I define a traversable of a file, and then I do some filters and maps to pull out the parts of the file that I want, and then I save that traversable view, and then continually iterate over it later. It will open a file, consume my input, do all my filters and things, give me just the data I want, and then close it when it's done. And I can do that every n times when I need to. That is a good pattern. But traversable is what you're looking for there. So you want traversable.view.
So you said that it lets you into traversables.
So if you consume into traversable, if you're calling map and filter and all that stuff, it will happen immediately and give you a new collection. But if you consume into a traversable but call .view before you actually do anything on that collection, everything that you do will be lazy until it has to go out and grab data. So traversable.view is what you want instead of stream. I do cover that in the book. So we can talk afterwards if you have concerns about traversable.view. We're improving views, but that actually it works out to be pretty well, or pretty efficient. Okay. All right, a little bit about Java integration, because that's kind of important with Scala. We're always integrating with other things. You should write your interfaces in Java. You can write your interface in Scala. If you write a trait that has no concrete methods, it turns into a Java interface, but it's usually just safer to write it in Java so people don't sneak in Scala concepts. If you sneak in too much advanced Scala, it's really hard to call from Java. Some of the really advanced Scala things don't look nice in Java. And if you write things that look like Java in Scala, then it's nice to call. But as your team gets more advanced with Scala, you're going to start using more and more of these advanced concepts. So just to be safe, define an interface in Java, extend it in Scala. You can instantiate the Scala class directly from Java, but you can make use of all these advanced concepts internally, and it doesn't confuse. You won't accidentally leak too much of the higher abstractions into Java. You should also prefer Java primitives and APIs. Why? Well, because Scala has its own collections library, and the Java collections library is actually kind of terrible for Scala because everything is mutable. If you take an array in Scala, arrays are pretty efficient. You can make use of all the really powerful Scala methods on arrays directly. So they come in nice. Same with primitives. If I define run to return an int, it's a scala.int. Scala tries to preserve primitives as often as possible. If I pass a java.lang.integer in Scala, I'd literally have to write java.lang.integer. It is not a scala.int. Even though Scala boxes and unboxes, if you use primitives in Java, they will show up as classes in Scala because Scala only has classes. Yeah? What? Array bracket string args is the type in Scala, yes. Oh, sorry, that should be on the other side. Yeah, bad slide. I just added that today. Sorry. Okay. Yeah, array string arg should be on the other side. Sorry, guys. It should look like this. Well, except instead of 0, call length. But yeah, that's what that should look like. Okay, so yeah, primitives come into Scala nicely. So now on to a little bit of functional programming. In functional programming, there are patterns from category theory that are useful. In OO, we have patterns like iterator, visitor, that sort of thing. In functional programming, we have patterns. They have funny names. When you become an expert Scala developer, you will no longer laugh at the names, but you might laugh before then. The first one I want to talk about is applicative functors. These are really awesome. If you remember, we had that example where I had I was taking in optional values. So option of a URL, a username, and a password. I want to get an option of a connection. There's this funny little @ method. This comes from a library called Scala Z. That's the method from Haskell. They don't actually provide human readable names for this, I believe, so you're stuck, but I think we should. Anyway, I can take the URL, the username, and the password and group them together and apply the driver manager.getConnection method. If you remember, driver manager get connection takes a URL string, a username string, and a password string, and returns a connection. So I am essentially, with this little funny at and apply, I'm grabbing out the underlying array character, I guess, and passing it to that method. So I'm joining computation. If instead of option, I had some sort of validation class. So I have a validation that returns a string, a validation that returns an int, a validation that returns a character. This is where I'm reading a form. I validate whether or not the form's correct, and I have an error message. Applicative allows me to take all those error messages and join them together, and the output of this will be either a joined error message or the resulting value. But the code looks the same. So this is how you can run some computation in a parallel fashion through some context. In this case, the context is option. Any sort of T of string that has an applicative functor can be that context.
So this essentially checks that URL, username, and password are not none.
Are not none. Yeah, that's all this code is doing. If I were using the validation library in Scala Z, then I could also, it would check that they're all not null, or not a failure. But if there were failures, it would join all the failures together so that I get a big long string of all the issues with whatever form came in. And I'm deferring that to later. So applicative functors take some values in some context, join them by a function, and give you the new value. So this is for parallel computation. And my brain just died. I had a good Java example of this kind of pattern, and well, sorry, can't remember what it is. So parallel join. I want you to, applicative functors, parallel joining computation. Anytime you use a for expression with more than one value, you are using what are called monads. That's a term that everyone thinks is funny. If you have a leaky abstraction with your monads, you have what I gave in a talk earlier called leaky monads, but we won't go into that. In Scala, we have a leaky abstraction for our monad concept. But in general, this is what monads look like. This managed, if you guys are familiar with Java, I think 7 added automatic resource management. So I want to make sure that after I use a resource, it's closed. Managed does this. It takes in a resource, and it will ensure it's closed when I'm done computing. It returns a managed of that resource, right? The type is some resource. So I can iterate over the input in a managed context. I can iterate over the output in a managed context. And then I can pipe the input into the output in my yield method. And what I get at the end is a managed context of this whole computation, serial, okay? We open the input first, then we open the output, then we pipe. If it all succeeds, everything's good. If there's any kind of failure, we ensure that the resource is closed regardless of failure or not. So there's some sort of a try-catch in this managed that will make sure that the resource is closed. So this is a monadic computation. It's a workflow. It's sequential. The first has to happen, then the second will happen. If input has an error opening, output will never be opened. But this is when you iterate over collections, you're doing monadic workflows. They're a little bit more confusing and abstract in that case, but this is essentially the monad pattern. For managed resource, I think it really makes a lot of sense, and you can apply it to other things. In akka, there are what we call futures. So if you know from Scala or from Java util collection or concurrent, I can pass some callable, and I get back a future value that it's going to compute on some other thread. I can actually use monadic and applicative on futures, and I can either join computations together that are happening in parallel, or I can sequentially wait until one future is done and then call another. What's beautiful is if you use akka as opposed to Java util concurrent, you can do it in a non-blocking way. So it will run the first input, pull it out, run the second input, pull it out, but that second input won't ever be sent until the first one's done, and none of this will block. You'll end up with a future at the end. It's a very, very beautiful pattern. I recommend you look into look into this. So if you look at futures and their flat map API, you'll see all that power. So that's the end of functional programming, and that is the end of the talk in terms of effective Scala, things to look into. I know that this was a fire hose, so I just wanted to give an opportunity for questions, if anyone has any. Yes?
Where did that pipe in? Was you that come from?
Yeah, you can assume I write those. So pipe takes an input and creates a pipe object that has an into, and then when you call into with an output, it will iterate over and do the piping. You can imagine you could have a pipe into method that takes an input and output. It's the same kind of thing. It's just not on the slide. Couldn't fit. Yes, anyone else? Okay, thanks guys.